We now move into the accelerated part of the talk, where each of the next speakers has 10 minutes each, so I won't waste time with an introduction. Roger Sharp is standing in for Rob Gordon. Go ahead, go for it. Thank you.
Yes, good afternoon. Standing in for Rob here. So I changed 45 slides down to about 18. So hopefully we'll get through them in this 10-minute slot. Been a very impressive conference so far, and this last day is no exception. You know, the new technologies and the things that have really changed in the last really in the last 10 years since 2007 are very impressive. The last two talks, you know, with the Armit sensor and the new loop design, similarly very impressive. So here we are. It's Quantec. Safety is very important with this GGSSA, this new initiative in the last 3 or 4 years down in Australia and percolating up into Canada. Very important for the electrical geophysics business. We're going to talk about Orion here. This is similarly the last 10 years of this move of electrical geophysics into 3D. So for Quantec, 2006, first development of the ideas, 2007, first deployment. It took until 2011 to get our first commercial survey. So it's a significant development effort in the first part of this decade, and since 2011, we've been surveying with Orion. So the Orion has all the fundamentals of Titan 24, which is the DAS, the distributed acquisition system, the time series recording, current monitoring. We couple it with MT, which is we feel is very important, and the last case I'll show you shows why the extra depth of investigation of the MT is really important in certainly in certain geological environments, but in a lot of them really, where people are, even when you've got a shallow target, the geologists that you're talking to are going to be talking about the drivers at depth, where the energy is coming from, and that's what the MT can show you. So when we started talking about Orion and 3D, there's a bit of an evolution here. The 3D codes came along, the inversion codes first. People started throwing 2D information into 3D inversions, and quickly realized that wasn't enough. There's not enough talk between a survey line here and the inversion that's happening over here, you know, 500 meters or a couple of kilometers away. So you need 3D data. So the next thing that happened was people started transmitting off the receiver line. So you have a 2D line deployed still, but now you're transmitting in an offset way to try and get some 3D component. There's problems there with near surface shallow coupling, and you start to lose some of your shallow information, but at the same time you're augmenting the 3D at depth. So what's the best of all worlds in our mind was to have an equal number of inline and cross-line receiver dipoles. So that's what's shown here. In the red, you see inline receiver dipoles, there's the red are the receiver dipoles. There's a north-south set and an east-west set. The same number in each. The logger is shown in the middle, and he's got 6 channels that he's measuring. And then we have some transmits associated with that are also organized in both dimensions like that. So this is the footprint of a typical survey. So you can see that we're in a very difficult access location here. That's part of the joy of the distributed receivers, is that you can deploy them anywhere. They don't have to be perfectly contiguous receivers. You can have some gaps if you need to go across faults or big cliffs or whatnot. And you don't have to have a perfectly regular grid square either, although this one shown here is. So here we've got a 7 by 7 logger deployment, which gives you 2.1 by 2.1 kilometer footprint of the main survey area. That size was chosen just to be compatible with Titan. because people expect from Quantec that you're going to be seeing deep, and because we've been advertising that for years, and so we're aiming for this 500 to 700 meter depth of investigation with this sort of a footprint. Here's an example of the transmit and the sort of the coupling that you get with the receivers. So again, inline and cross-line receivers shown in black, the loggers in green, one transmit in red. And the idea with these ray paths is just to kind of give an idea of the different coupling directions. We're calling this an omnidirectional coupling, such that there's no conductor left untouched by even one transmit here. And when you put another transmit, you can see things get complicated pretty fast. You're going to have to invert this data. It's going to be very difficult to just look at raw data and understand what's going on. So here's a comparison with 2D and 3D. So the 2D is shown in green. It's shown as pseudosections tipped up with a gap in between the pseudosections, with the idea that this is the sort of volume that you'd be investigating with these apparent plot points. And there'd be a little bit of a cone, a little bit of overlap at depth, but certainly at the shallow depths, you're not investigating much in between the survey lines. And then because we're tipped up here, we've got an Orion distribution similar to that 7x7 that I was showing you on the previous slide. He's deployed at surface there, and then we're just showing 3 transmits. So one in blue, we've got a transmit in one corner, and you see this kind of blanket of apparent plot points coming down towards the center of the survey area. And in the other corner, similarly, this blanket of apparent plot points reaching across to the receivers that are on the other side of the block. And if you transmit right in the middle, then you get this kind of cone of apparent plot points, some very shallow, and the rest stretching out towards the receivers that are at the edges of the block. So when we do all 500 transmits for 300 receivers, this is the sort of apparent plot point map that we're going to generate. It's a lot of information for the inversion, but it's not just a lot of information. It's a lot of unique information that completely fills in all the gaps, and you get information from every cell, every area on your underneath your survey area. So this is the value of the 3D. Since 2011, 20 surveys under our belt. We've got a couple more that we'd be pleased to talk about in the next future conferences, but let's show a few quick case histories here. This is Hidden Hill, our very first commercial survey. What we're doing here, thank you, is showing very high resolution. So we've got 200 meter resolution here. These are drill holes shown in a resistor. So I've got to move fairly quickly here. This is the opposite, where we've got a 700 meter target, an iso shell of chargeability, and you can see drill holes again. When the drill holes intersect that iso shell, you've got anomalous results in the drilling, and when they're outside the iso shell, there's no result. So good correlation with geology. Here, similarly, this is Phoenix. We're up in the Athabasca Basin. We're looking underneath the unconformity at 400 meters depth here. And we can see there's foliations plotted on top of that sort of central bigger plot that indicate the good correlation of strike directions that are a little bit unexpected, but at the same time match very well to geology. And then our sort of premier case history here with the MT. So here's a porphyry system that's going to benefit from really seeing deep. You can see the white alteration on the hill there, down in South America. Here's our deployment of loggers. This is at pushing 5,000 meters, and so very difficult access. You can't make contiguous dipoles, but that still ended up being okay. Here's our nice inversion block. You can see the kind of annular features associated with the near surface epithermal part of the system, and then as you go to depth, you get into the big cuprite blanket on top of the hypogene that is sitting on top of the big porphyry system, and the driver that would be underneath it. So here in the resistivity, we can see that a little bit better. You've got the epithermal quartz veins at shallow depth. You've got a big conductor associated with that hypogene, and then you've got the MT drives the resistivity right down into depths that we're imaging the actual root of the porphyry here. And you can see the classic zonation from the conductive neck out into the resistive alteration halo. So Orion, accurate for imaging complex environments from shallow depth, very high resolution, all the way into the deeper depths where you get the penetration to look at those drivers and really know what's going on. Thank you.